Good afternoon. Can you hear me?
Yes, good afternoon.
Great. Thank you so much. So a few things first. First of all, I already posted the grades and solutions for project 1 and exam 1. That concludes our section 1. I would like to give you another chance to review these exams, to review these tasks with me. So what I'm trying to set up is perhaps an office hour tomorrow. So my thought is perhaps a office hour on Tuesday, that is October 6th, 3:30 to 4:30 p.m. You can use the same Zoom link. I'm gonna post the announcement right after this lecture. So during this office hour, you can ask me any questions you have related to exam 1, project 1. If you don't understand any of those questions, you can join in, or if you have any concerns or questions about your grades, also you can also stop by. And today we're going to conclude everything you need to know about exam 2. So if you do have any questions related to exam 2, you can also stop by during the office hour. All right. So the second thing is project number 2 has been posted, and then there is a special function in these problem description. It might not be clear to everyone. I want to emphasize it. So this is a sign function. What does it mean is if your input x is positive, then gives you a value of 1. If it's negative, then returns a value of -1. If it is 0, then the value is 0. So that's the meaning of this sign function. There is a built-in function in MATLAB, and I believe it is called sign, so you can directly use the function to generate that curve. The third thing is about ODE 45. I noticed this challenge in your exam number 1. So the last question is actually pretty divided. If you know ODE 45, most of you get 20 points. And if you don't know, then most of you actually lose 90% of the points. So I think I didn't do a good job teaching you how to use ODE 45. So in the end of this lecture, I'm gonna explain ODE 45 a little bit more. I also posted quiz number 4 on Blackboard. So I have 3 different small tasks over there in the quiz 4. Try your best to answer all of them. And I'm gonna post solutions by the end of Thursday. And if you have any questions, I might have another office hour scheduled on Friday, just answering your questions related to ODE 45. All right, just pay attention to the announcement. I think that should be it. So that's all the things you have to, that's all the announcements before the lecture. So I think before running into these seismometer and accelerometer systems, I would like to give you a brief summary of what we have learned right now. So in section 4, we start from a set of ODE, right? We start with a very easy first order ODE with harmonic excitation. So the ODE looks like something like this. And then if we want to normalize it, then your ODE looks like something like this. So that's your ODE function, or sometimes we call equation of motion. So that's the first concept. We also learned the second concept, which is called steady state. So steady state is a solution of your xt, and then it looks like something like this. So we call your A magnitude, or you can call it amplitude. Your theta is the phase lag. So your steady state and ODE, they coupled by the solution of the ODE. So your steady state is XPT, which is the particular solution. Right? So that means your steady state is only part of the solution of your ODE. So your ODE, actually the solution has two parts. The first part is called homogeneous solution. The second part is called particular solution. But as we recall, in previous lectures, we explained that these homogeneous solution corresponds to a so-called transient state. Eventually dies out because of the damping of your system. So if time is long enough, eventually your xt becomes a particular solution. So we call these, eventually we call this final solution the steady state. All right. So in this lecture, in this section, we're talking about if the ODE is given, how can you find the steady state? So solving the ODE, find the XP is one option, but it's not the most convenient one. So that's why we introduce two other concepts. The first concept is called transfer function. And then the second concept is called Bode plot. So these two, even though they have two different names, but they're actually connected. They actually represent the same thing in just two different ways. So in transfer function, we represent everything in S domain. For Bode plot, we represent everything in omega or in frequency domain. So here I'm going to use this table trying to explain how these four concepts are connected. All right. So what is transfer function? So from ODE to transfer function, the method is called Laplace transform. How do you do Laplace transform? You just first identify inputs and outputs. And then you convert time derivatives to as operators. All right, so let's use this ODE for example. So x double dot, your constant stays the same. Let's using the normalized format, so everything is consistent. Your x double dot becomes xs. Your second order derivatives becomes s squared. The same thing applies to the second term. The constant stays the same. First derivative becomes a single s, and then time domain function becomes s domain function. And then the third term is omega n squared, s domain function. And then in this case, let's assume your output is xs, your input is f. So that's why whatever on the right-hand side is your harmonic force. So you should treat this entire thing as the force, a force function. So that's why on the right-hand side is directly fs. Okay. So then you move things around. Your transfer function is output divided by input. So in this case, it's xs divided by fs. And then that's s squared plus 2 omega n zeta s plus omega n squared over 1. So that's your transfer function, all right? So that's how you go from ODE to transfer function. So let's focus on our steady state. If you look closely, you can actually see that the magnitude A is a function of omega. Your phase lag is also a function of omega. So that means the steady state amplitude and steady state phase lag depend on the driving frequency. So if we want, you can actually plot these two responses. So it's as a function of omega, that's your amplitude A omega. And then here's the function for your phase lag. So the phase lag would be something like this. And then your magnitude would be something like this. All right. So that's your body plot. So if you have, if the body plot is given, then from body plot to steady state, that's pretty straightforward. Because in order to find your steady state, you just need to find the magnitude and you just need to find the phase lag. What you do is, once your excitation frequency omega is given, let's assume that in this case, your omega is omega naught. So that means whatever value you get here is gonna theta omega naught. And then whatever amplitude you get here is A omega naught. So these two values directly determines your steady state response. So that means you can directly calculate a steady state response from body plot. But how can you get body plot? So that's the coupling between transfer function and body plot. So between these two, what you need to do is just replace S by omega J. Once you have this transfer function, you replace S by omega J, and then you're going to get a complex number. And then the norm of this complex, let me write it down here, is the norm of the complex number. Let's define this complex number as, in this case, is omega J squared plus 2 omega n zeta omega J plus omega n squared over 1. So after replacing S by omega J, you get a complex number. So your A omega is just the magnitude, is just the norm of this complex number. And your theta omega is the angle of the complex number. All right. So here we complete the loop. So that means in section 4, you're going to see 4 different things. You're going to see the original ODE. You're going to see transfer function, body plot, and steady state. Remember that the ultimate goal, this is our goal. The ultimate goal is to find the steady state response of your system. But most of the time, we start with ODE. So to simplify our calculation, that's why we have to go through the transfer function and body plot route.
So with the body plot, so A is just going to be like the magnitude of the wave or of the function in that point in time, and the theta is just going to be somewhat like the direction. Is that kind of an accurate?
I think I made a miss. I need to clarify a little bit. So actually, this C start is not directly the amplitude and phase of A. It's actually the ratio. Your C star is the ratio of your X over F. So the phase will be the same, but then in order to get to A, your A omega is actually the amplitude of your excitation times the ratio. I would say times the excitation, right? So in other words, your A, once it's multiplied by the amplitude of excitation, then it's directly the magnitude at steady state. And then your theta is a phase lag. So that means your response won't be immediate. If you apply the sine wave, then your response will be slightly slower than your excitation. Then how much slower, that is defined by your theta. Oh, sorry, I interrupt your question. Could you repeat it?
No, that makes sense. I was just kind of double checking if that theta is somewhat just like the direction of the function in that point in time. That was all I was mainly asking.
So in the end of this lecture, I'm going to explain these dynamic measurement of damping. Then you can see how the damping how the theta comes into play.
So,
all right, so
is C star the transfer function?
Yeah, C star is the transfer function, but the S is replaced by omega J.
Okay, thank you.
Yep. So here I just want to show you the connection. I'm going to use the accelerometer to explain how to implement these flowcharts. All right. So if you have no time to take notes, I'm going to share these after this lecture. So here's another base excitation problem. You've already seen these in previous 2 lectures. I'm going to skip the derivation for equation of motion. That's the equation of motion you're going to expect. You can normalize it. So you can normalize it by m, and then you have the standard format. All right. So we already talked about the base excitation in y and x. So we have defined force transmissibility, displacement transmissibility. Here we're going to make changes. So we have the same ODE, but we define different outputs and inputs. In this case, in the first case, we assume our input is y, or displacement. And then we assume our output is z. Your z is x minus y. All right. So basically, your z is the relative deformation. In practice, the easiest way is you have a pointer. Inside of these casing, you're going to have a potentiometer. And then as this pointer moving up and down, you can measure the relative displacement z. All right. So if you replace x minus 1 by z, then your ODE becomes z double dot plus 2 omega n zeta z single dot plus omega n squared z equals to minus let's see, minus y dot, y double dot. All right. So as we can tell here, the input is displacement, output is z. We want to find the steady state response of the variable z. So that's why we have to find the transfer function, right? Remember the final destination on the right, top right corner. We want to find the steady state. Then we need to find, let's assume y is y naught cosine omega t, And then we want to find out the ZT steady state equals to some Z naught cosine omega t plus theta. We want to find the phase lag. We want to find the amplitude. The frequency will be the same because it's a linear system. All right. So in order to find the Z naught and theta, we need to first find the transfer function. The way we do it is we replace all these time derivatives by S operators. So it's S squared ZS plus 2 omega zeta S ZS plus omega n squared ds. And then on the right hand side is minus ys s squared, right? And then you can move things around. You have your output over input. That gives you your transfer function. Minus 1. So once you have your transfer function, remember that flow chart. The next step is we need to find out the Bode plot. How we do it, we just replace the S in the transfer function by omega j, and then remember we define these as a complex number C, and then that is minus 1. S squared is omega j squared, 2 omega n zeta. S becomes omega j and omega n squared. And then you can collect all the real terms, all the imaginary terms, and you have minus 1 omega n squared minus omega squared plus 2 omega n omega zeta j. So as you can see here, that's a complex number, right? So how can we find a Z naught and theta? In order to find a Z naught, we don't know the Z naught, but from this Bode plot, we can easily calculate the Z naught versus Y naught. We know the ratio of these amplitudes. The ratio of these amplitudes is directly the norm of this complex number. All right.
Just one
Yep.
quick question. So
Mhm.
I'm sorry, I'm just trying to catch up here on the transfer function. So when if you want, can you scroll up to the smidgen?
Yep.
So with the negative, so I don't know how we got from like when we were converting all our x terms to z terms.
Mhm.
Why are we only left with the negative y double dot term on the right hand side?
Gotcha. So if you just replace all the x minus o, let me use the red line to underline this, okay?
Okay.
So you have no problem with this one, right?
Nope. Yeah, that one makes sense.
So what you can do is you can plus y double dot minus y double dot, right?
Right.
And then you move whatever in the bracket to the left-hand side.
Oh, okay, and I see. And then those all become z's, and then what we're left with
Yeah,
is
those all
negative y
become
double
z's,
dot.
and then minus y double dot is left out.
Okay, and then okay, I see. And then why didn't the y term, when we were converting them all from time domain functions to s functions, why didn't the y become like? How do we get rid of the y when we go down to the transfer function?
Yeah, I think I understand the question. So that all goes back to your definition of output or input. In this case, our input is displacement. So that means in the transfer function, you want displacement in the denominator, right? So then you cannot treat these acceleration as a whole. You have to go back to the definition minus dy twice, dt twice. So that means on the right-hand side, you have to leave the S domain function for your displacement, y.
Oh, okay. I see. Never mind.
It's different from these accelerometer definitions. So right now we're only talking about so these derivation here, I think I need to make it clear. That's for seismometer.
Right. Okay. Sorry. I'm sorry. For a second, I guess it's just the week and where that, passed by. I see where you got the YS over there. Okay. That makes
Yep.
a lot more sense.
And then we're going to talk about accelerometer later. Then you're going to see the difference. Actually, there's a very, very crucial difference. A lot of students get confused in the exams when I change the input definition. All right. So
I have a
once you have
question.
these, yep.
What happens with the S squared term next to the Y?
Oh, I see. I think
Oh,
you got a good catch.
Okay.
That's a minus S squared.
Okay.
Sorry. Yes, I myself got confused. So you have an omega J on top.
it's an
So
excellent.
that should be, yep, that should be positive omega squared. All right. So if you go back to my lecture notes, and if you look at the textbook, they use a variable R. So what they're doing is they define a relative omega. So they divide the driving frequency by the natural frequency of the system. So what you're doing here is just you need to divide it both the top and bottom by omega n squared. Then you're going to have R squared, 1 minus R squared, plus 2 zeta Rj. So the benefits here is instead of using two variables, you're getting one variable. You're using one variable to describe the frequency. And then this R variable is unitless. So if in the exam, you can just stop here to calculate your steady state response. So this complex number gives us two things. So first of all, the norm of this complex number is the ratio of the amplitude. Okay, how to calculate the norm? If you have MATLAB, then you don't have to worry about anything. But without MATLAB, what you do is you calculate the norm of the denominator divided by the norm of the, and then norm of the numerator divided by norm of the denominator. So it's just the square of the real part plus square of the imaginary part, and then take the square root. So that's everything in omega. If you calculate everything in R domain, that's just R squared over the real part plus the square of the imaginary part. So that's how we got these equation there. So these give us the ratio. So remember in the exam, if I ask you for Z naught, your Z naught is always the magnitude times Y naught. Don't leave out your input magnitude. All right. So the second thing is, yep, go ahead.
So just a quick thing. So when we converted the imaginary omegas into the real omega. In the denominator, it says 2 omega n times omega times the dampening ratio. And then is that a J term?
No, the J is left out. I think that all goes back to the very beginning. I think in one lectures I explained that. Let me do it again. If you have a complex number like this, the norm of this complex number is square root of A1 squared, B1 squared. So in this case, whatever in front of the J is a B2. So your J is left out.
Gotcha. Okay.
So it's slightly different. So I think in mathematics, sometimes you want to move the J to the numerator, then you multiply the numerator by, you multiply the denominator by this conjugate. So that's actually slightly different. So when you calculate the norm, it's different from calculating the, it's different from multiply it by the conjugate. So you have to use these relationship. All right, so the second part is what is the theta? Your theta is just the angle of this complex number, right? So in this case, your top is positive value, so 0 degree minus the arctangent, the imaginary part divided by the real part. So I can actually extend this relationship a little bit. So the angle of this complex number is tangent invert B1A1 minus tangent invert B2A2. So if you look at our case, so our B1 is 0, your A1 is a real number, so that means this invert tangent of 0, that's 0 degree. And then you minus whatever angle in the denominator. So that's your theta. So if you want to reconstruct your steady state response, your ZT, let's put a particular solution there, and it's going to be Z naught cosine omega t plus theta. So that's something you have to pay attention here. If you use my method, here should be plus. So if you look at the textbook, they use minus. So that means all your phase will be 180 degree off. So just keep consistent. Either method is going to work, but you have to keep consistent. So that means if you have plus theta over here, then you're using my method. If your ZP, I'm using different color. If your ZPT is Z naught cosine omega t minus theta prime, that means your theta prime will be minus theta. Right. So that's when I give you an ODE, I ask you, and the driving frequency is already known, and then I ask you for the steady state. That's the method you use. There's another way. So when you want to, so that's actually what we do for system analysis. When your system is already given, you want to analyze your system. So there's another type of questions when we want to do system design. So let's look at these seismometer problem. So let's plot these transfer function, only the magnitude. So then we're gonna have a plot like this. Let's focus on this plot. All right. So your plot would be like something like this. Whenever you want to do design, so that means we need to design your M, C, K, or you want to design the omega n and zeta. How should we choose MCK and omega n zeta? Remember, that's a seismometer. So that means we want to use this device to measure the base displacement. All right. So how to define a good sensor? So that means your output, Z, is linearly related to input Y, right? That's what a good sensor does. So a sensor should give you a constant sensitivity. So in this case, your Z over Y, that we call it sensitivity. You want this sensitivity to be a constant value, otherwise your sensor won't work. So let's look at our curve. So definitely you want to work in this high frequency region, right? So that's when you have a flat curve, or when your Z over Y ratio is a constant value. So which means your seismometer should have we should work at the high frequency region, or we should work on the right hand side of the natural frequency. So remember that your natural frequency is omega n, or is square root of k over m. So that means you want this omega n to be as small as possible, right? So if this stands, that means this width here can be reduced. We want to reduce this width. So how can we do that? So that means you want to use a soft spring. You want to use a large mass to reduce the natural frequency. So that's why if you're using seismometers, then usually the device is huge. That's because of the large mass on top. And then if you're interested, you can search like the so-called geophones. So researchers in geoscience department, they use this a lot to measure the earthquake. And then these devices usually bulky. And the other thing is you also want to follow these dashed line, right? Compared to these solid line, you actually want to follow the dashed line to get rid of these low frequency resonance. So by doing so, you need to increase your zeta. In other words, combine these two, you want higher damping, you want larger mass, you want lower stiffness, all right? So I might ask you similar questions during exam 2. So you need to plot the frequency response and then have a brief discussion. So any questions? If no questions, then let's talk about accelerometers. Let me write this out. Let me copy and paste the transfer function. Oh, sorry, the ODE. Let's directly copy the Z double dot. All right. So because it's accelerometer, then our input is different. We're no longer measuring the displacement. We're measuring the acceleration. Then the input is going to be y double dot. If you want, you can replace it by AT, just for convenience. And then your output will still be the Z, because then we're going to use a potentiometer to measure the relative deformation. All right, output input. So that means our transfer function here is different now. Your input, your output is still Z, but then your input will be AS, right? Because we're no longer doing so we okay, I can answer that quiz 4 question later. So the transfer function is Z over AS, and remember that that is a minus AS minus AT. Oops. Okay. So personally, my preference is you're going to replace what you're going to put the actual inputs into your equation so you can get rid of the confusion. Because if you go back to the seismometer problem, because our input is y, so you want to leave the y in the ODE. But here, because our input is actually acceleration AT, so that's why you actually want to replace your y double by AT. So after doing so, what you have is minus 1 over s squared plus 2 omega n zeta s plus omega n squared. Okay. And then again, what you can do is you can define a complex number C by replacing S by omega j. So it's minus 1 omega squared minus right? So if you want to calculate the Z naught over A naught, your A naught is amplitude of acceleration. And it's just the magnitude of your complex number. And then your phase, remember that your phase is just the angle of these complex number. And then in this case, your ZT would be Z naught cosine omega t plus theta. Okay, I think there is a typo in the lecture note. So you have to, if you want to normalize everything that is on the denominator is actually 1 divided by omega n, or let's see. Yes, it should be 1 divided by omega n squared. Oops. So here, the numerator shouldn't be 1. It's actually 1 over omega n squared. So how can we implement these body plots for design? So let's look at our body plot. So here, again, we want to design MCK or omega n zeta. We want to design the system such that we get a good accelerometer. So that means the design requirement or design target is such that your output Z is linearly related to input AT. The same thing, you want a linear relationship, so you want the body plot to be flat. So let's look at these curves. We have 3 different omega values. So the first thing is you want the omega to be around 0.7. It's actually 1 over square root of 2. So by doing so, you're not getting a resonance, or you're not losing the frequency of bandwidth. So this one is your best design. The second thing is you actually want to work in this region. That's when your body plot is flat. So that means you want, so this location is determined by omega n. So for a device, in this case, you actually want your omega n to be as large as possible. So that means you want your m to be small, you want your k to be large, and then your c is designed such that your zeta is 0.7. So that's the design. When you design accelerometers, that's how we select parameters. So it's very different from seismometer. So for instance, in this case, you actually want higher stiffness, smaller mass. So that's why accelerometer is very small. So if you look at, I used to have a video showing your accelerometer in your cell phones. So they call these MEMS device. It's actually micro scale. So that's why accelerometer is much more common when we in vibration measurement, right? So that concludes the transfer function discussion. So I'm gonna briefly go over your quiz number 3, because after checking your solutions, I have some concerns. So hopefully after these, you have a better understanding. So any questions up to this point? So my comment is yes, I can extend the deadline for quiz 4. Perhaps even extend it to the end of Sunday. But the office hour will still be Friday. I would like to give you more time to prepare for exam 2. I just want to make sure everyone knows how to use ODE 45 before exam 2. All right. So after that, let me see. I don't know if I should move on to this news topic. All right, so I'm gonna give you a very quick overview of this dynamic measurement of damping. That's critical for your project number 2. So let's recall we have a system, a linear system. And this linear system is harmonically excited, is a harmonic excitation. Let's assume that your Ft is F naught cosine omega t. So what we're doing is we want to create a 2D plane. And then your x-axis is your force excitation. Your y-axis is your response. Or if you want, I can also put these original format by the side. That's actually a small ft. Oops. So let's start from a very special case. When c equal to 0. So then your function becomes x double dot plus kx equals to ft. And then also your omega is small. So if it's a static excitation and then no damping, so what you're gonna have is a linear line, right? That's your elastic performance. If you remember your mechanics of materials class, that's basically the elastic region of your stress strain curve. But once you have damping in your system, so things becomes tricky. So as I said, once you have damping, then your response is going to be slower than your force. So you're going to have a curve like this. Why? We got this curve. That's because once you apply an F, you're not getting this response. You're getting a response slightly smaller than that elastic response. So that's why your curve is going to be it's going to be lower than the purple line when you increase it, when you increase the force. So the same thing, if you want to reduce the force, your strain response is going to be slower than the elastic performance. So eventually, you're going to get these counterclockwise curve, and then these counterclockwise curve indicates energy dissipation. So we call these curve hysteresis. You're going to see this a lot if you work with rubber or any elastomer materials. So the area enclosed by this loop, we call it delta E. So this delta E is your energy dissipated per cycle. All right. So from this delta E, you can find your C coefficient. Your C coefficient is just delta E over pi omega x squared. And I'm going to give you your x. Big X is just the amplitude of that loop, which is the maximum value of that loop. All right.
And to double check, the project, I believe this is what, parts 2 and 3 of the project, number 2?
Hmm.
Gotcha.
You need to find the area of this shaded loop, this enclosed loop, and then once you find the data E, you know your excitation, you know the pi. You can easily find out the magnitude. Then you can find out your equivalent damping ratio or damping coefficient.
And do you want us to create a function or like a graph similar to this showing the force relative to the displacement like this?
If you want, yeah, that's going to help me to grade,
Okay, perfect.
but it's not necessary. So that C equivalent is one thing. So that means this definition works for any kind of damping. So it's not only for viscous damping. So for example, if you have friction, if you have nonlinear damping, if you have like air dragging or something we discussed in the next slide, you can always use this method to find out the equivalent viscous damping coefficient. So that actually helps you to simplify a nonlinear system into a linear system. So that's very, very common if you have rubber in your mechanics system. And the rubber is a nightmare if you want to model it. This provides a convenient way to deal with elastomers. So the next thing is about a complex stiffness. Let's go back to this mx double dot to omega n psi. So we can assume that your x is a big X E j omega minus t minus theta. Oops. Right? Then your x single dot is j omega t minus theta, right? You can replace your x and x dot and plug it back. By doing so, then you can get rid of your x dot term. So what you have is x double dot equals to 2 omega n zeta j omega plus omega n squared x equals to ft. So these, whatever in front of this, we call it complex stiffness because it's a coefficient in front of x, but it's no longer a real number. It has j in it. So that's why it becomes a complex number. So perhaps I shouldn't using these standardized format. So this complex number in front is called the complex stiffness. So your complex stiffness is 1 plus eta j times the real stiffness. Your eta is unitless, and then is called loss factor. Again, if you're gonna work on rubber in the future, then loss factor is most commonly used to describe the damping. All right, if you only care about the project number 2, this is the only equation you need to remember here.
Wait, won't we also need to remember how to calculate the delta E as well?
Yes, the delta E is a shaded area.
As I say,
I would like to challenge you at least for 1 week. If you still have trouble calculating this area, let me know. I can give you an explanation. The hint is you have to do integration. So the shaded area theta E is so you have to figure out how to calculate these derivative, these integral in MATLAB. I think if you have like individual data points, like if you want to do it digitally, then I think it's trap Z or trap Z. I always forget which one. So either one of this, I think is trap Z. So that helps you to calculate integration.
I was gonna say, also when it comes down to if we use trap Z, that's just gonna be taking it from a graph, correct?
Yep.
Versus if we want to do the integration manually, or using capital X, can we calculate the capital X and then just calculate it doing pi times C times omega times X squared?
I don't think you can do that. Because if you have a nonlinear system, I don't think you can calculate these analytically. So that's why, so the flow chart of these project 2 is you first want to use your ODE 45 to find, so you already know your FT, right? You want to use your ODE 45 to calculate your XT as a function of FT. And then what you need to do is you find your FT, XT numerically, and then you calculate the shaded area through some numerical function, which is trap Z. So I don't think there is a way you can do these analytically. I don't think so, because your damping is nonlinear. It's actually discontinuous. So no worries. Let's try to challenge yourself on MATLAB, and perhaps next Wednesday, if you still have questions about how to calculate the shaded area, I can provide you an example. All right, so I think I have another 15 minutes. Perhaps I won't have time to go over quiz 3, but I already posted the solution online. So after today's lecture, hopefully you can understand. And I would like to spend a few minutes discussing ODE 45. So if you already know how to do it, then you don't have to stay. Let me pull it up. Can you see my MATLAB screen?
Yeah, we can see that. So
but it's in the workspace. Let me see.
they just posted a picture of just what I'm getting output for project 2. Is that kind of what we're looking for just like that first portion?
Let me see. How should I do it? Did you post it? Where can
Yeah,
I
I
see your
just
picture?
posted like a JPEG.
Oh, I see.
Where there's like in that it has like a transient and steady state as far as I can tell. Is
Yes, you're correct. Oh,
Okay.
yes. Actually, that gives me another hint. I forgot to mention. So when you calculate these shaded area, you have to make sure your system has reached a steady state. So that loop is a steady state loop. You have to get rid of. You have to truncate the steady state response before you plot the loop.
Okay, cool. And then of course during that course we'd want to also set make the force as a function of time, and then we'd come.
Yep.
Okay, gotcha. And then we can use that as our x-axis, and then we can use the y-axis as our steady state response, right?
Yep.
Awesome.
See.
Awesome.
Share screen. Okay, here's the screen. That's the correct screen. So that's the clue number 6 in example 1. The ODEs, there are 2 challenges. The first one is I flipped the order of these state variables. So in my lecture notes, your velocity is in front but then here I flip it. The second thing is there is a nonlinear equation in part 3. So what you do is in your ODE 45, Ty equals to ODE 45. You need a function. This function is dy t span y naught. So let's forget about the options. I want to simplify everything. So what is the dy? dy is the changing rate of state vector described in y. So you have to describe the changing rate of your state vector using the state vector. And then t span is the time span when you want to calculate response. Right? So t span is like the range. Like, because it's a numerical method, you have to define up to which time point you want to calculate your response. And then why not initial conditions of state vector. All right. So always remember what. So the first step is, yes, I'm going to publish these as well, and I'm going to post. So, yep, yeah. To be in short, yes, I'm going to publish this. So the first step is you have to define on your notebook or you need to pick a piece of paper, define your own state vector. All right. So the order of these entities, it doesn't really matter. You have the freedom to change the order. So let's use displacement and then velocity. So that means your y naught is first initial displacement and then velocity. Your displacement is minus 0.05. The second entity is the velocity is 0.1. All right, so that's your initial values. Your t-span is in which time window you want to find the result. So here I mentioned is from 0 to 30 seconds, and then let's use 301 points. Okay, so that's 0.1 second per step. So you so my suggestion is at least 20 points per cycle. You have to estimate your omega n first, and then estimate your period. You need to make sure there are at least 20 points in one complete cycle. Otherwise, you're going to see the Nyquist effect. You are going to miss the high frequency information. All right, so why not t-span? They're very straightforward. I think the challenging part is how to find the changing rate. All right, let me type it out. Insert equations. So your dy is y dot, okay? And then y dot is going to be a column vector. Zoom up. So remember, the first one is displacement. So that's what displacement becomes velocity. Your velocity becomes acceleration, right? As I mentioned before, you want, as I mentioned in this comment, you want to use your state vector to describe the changing rate. So that's why in the right-hand side of your equation, you can only have x or x dot. So what is x dot? The first one is easy. Your x dot is directly x dot. But then what is your x double dot? Then you have to go back to your ODE. Okay, so you can get your, you can describe your theta double dot by theta dot and theta. So what you do is just move everything to the right-hand side. You're going to have minus x oops, let me see, minus 0.5x minus 0.15 dot x. So I think I may get you confused a little bit. So actually the x here is the same as theta, okay? So here, that's up to this point, that completes this line. So we described the changing rate of y by using only x and x dot, by only using the variables inside of the state vector. Okay, so what you can do here is then you define a dy function. Your input is always t and y. Your first input is time, second input is a state vector. And then as we know, your dy is a 2x1 vector. So the first entity is just y2, right? Because x dot is the second entity in your y. And then the second entity is 0.5 times y1 minus 0.15 times y2. Then you just need 4 lines. You're going to get your response. So eventually, your t is a column vector of including all time points. And then your y is a m×2 matrix. So the first column is the result of your first state variable. The second column is the result of the second state variable. So that means your y is going to be an m×2 matrix, and then your time is t is m×1. So n is how many time points you have. So if you want to plot displacement, then you have to go back to your state vector definition. That your displacement is your first entity. So that's why if you want your displacement, that is your first column in your y matrix. If you want velocity, that is the second column of your matrix. Okay, so let's plot it up. Displacement, and then give it a shot. You're going to see is a underdamped response, free vibration. Eventually it's going to die out, and then the amplitude is decaying exponentially. All right. So in this question, I asked you to write your dy as a matrix multiplication, but in practice, that's not necessary. So you can only do these when your system is linear. For example, if you're in your part 3, you will never be able to find the A matrix because you have a nonlinear system. So let's name these as part 1. Let's replace these and then calculate part 2. Same thing. For part 2, you have your initial condition, you have your time span, that these two are the same. Your ODE 45 would have the same input, same output. The only difference is your changing rate. So let's look at our changing rate. Your y dot is still x dot over x double dot. And then the first entity is still velocity, but then the second one, it's no longer single theta, it's actually sine theta. So that's why you have to replace these by 0.5 sine theta. Or if you want, it's sine x. So you don't care if this function is linear or not. As long as you can describe your change in rate by x and x dot, then you don't even care about what the function looks like. So here in this case, so you change these y1, that's your theta, to sine theta, right? And then you can run the same thing. And the response should be very close, almost identical. That's because your theta is very small. The small angle assumption should always stand. All right. So actually, I can extend these a little bit. What if you have, so since we already learned how to do, oops, insert. What if you have x 2 0.3 plus sine x equals to 2 times cosine t. Okay, so let's calculate. Let's name it case number 3. I'm gonna clean up this code later, so no worries. So for case 3, your left-hand side is the same as part 2, but then on your right-hand side, you have a time-dependent function. But no worries. What you can do is, you still have the same state vector and also the time span, but your changing rate is changing. Your velocity is still velocity, but your acceleration is not only a function of velocity and position, it's also a function of force. So that's why you have to add the force term on the right-hand side, right? So that means you can describe your changing rate as a function of state vector and also a function of time. So that means you just need to add a cosine t term in your dy. And then let's see how it looks like. You're going to see that's transient state. Eventually, you're going to stabilize. If you want to see the steady state response, we can set the time longer. Because then you can see the response stabilizes, and then that's your steady state. All right. So up to this point, because we're only talking about single degree of freedom systems, so that means you can copy and paste most of the code. The only thing you have to change is this dy line. Just make sure you describe your change in rate using state vector and using the time function. All right, so please complete quiz number 4. If you have any trouble solving quiz number 4, let me know. We're going to review these together on Friday. I'm going to send a Zoom invite to everyone. Just pay attention to the Blackboard announcement.
And that's the quiz 4 is going to be postponed till like the due date, that is, till
Saturday. The due date is going to be the weekend, but Sunday, I'm going to review that problem on Friday.
Okay, excellent. Thank you. Yeah, it helps to have the option to work it on a little bit on the weekend because, you know, weekdays can be just so busy.
No worries. For me, like quiz is more like a quiz for myself. It's not for you.
No worries. I mean, they're definitely a learning experience too, because like this last one is like I looked over your solution a little bit and I see where I went a little wrong on like the transfer function and stuff like that. But having that is very helpful to learn from.
Cool. Yeah, and I think exam 1 actually warned me a little bit. I mean, yes, I think I have to spend more time on MATLAB. So, yeah, before exam 2, I hope everyone will be on the same page.
All right, thank you for your time, Professor.
Thank you. Nice to talk to you.
Indeed, likewise. Have a great day. See you Wednesday.
Yep, see you. Bye.